Did you know you don't need millions of dollars or hundreds of GPUs to fine tune today's most powerful language models? Thanks to techniques like LoRA and tools like Unsloth, you can adapt models like DeepSeek R1 on just a single GPU. And today I'll show you exactly how. So, before we get into the code, let's just step back and ask why fine tune a large language model at all? Well, large models like DeepSeek or Llama are trained to be generalists. So they know a little about everything, but not enough about your specific use case. So you fine tune when you need domain expertise, like medicine, finance, or law, or when you want consistent behavior, since the base model may sometimes drift or hallucinate. So fine tuning is about making a general model into a specialist for your problem. Now, there are different ways to fine tune a model, and they come with trade offs. First would be full fine tuning, where you retrain all of the model's billions of parameters. This gives the best accuracy but is super expensive, and you need multiple high end GPUs and lots of data for it. Next would be LoRA, that is low rank adaptation, in which instead of changing everything, you only train small adapter layers inside the network. It's way cheaper, requires less compute, and still gives excellent results. And that's what we'll be using today. Next would be prompt tuning or prefix tuning. Instead of touching the model, you just learn a set of special prompt tokens that guide it. Think of it like giving the model a cheat sheet. It's fast, lightweight, but less flexible. Alright, then let's begin with the tutorial. I'll be walking you through setting up your environment, loading and preparing data, performing base model inference, fine tuning the model for advanced medical reasoning based on our instruction set, comparing the before and after results, as well as saving, pushing, and merging your fine tuned model. So let's dive in. For this, I'll be using Kaggle since it provides a GPU for free. And let's start by installing the key packages, which is Unsloth. Now, Unsloth is a really great toolkit that gives us faster training and inference for large models. Next is importing the dependencies and configuring some crucial hyperparameters. Over here, max seek length means it's a parameter that stands for setting the maximum number of tokens that the model will be able to process in a single input sequence. Now, the reason why it's there is because transformers usually require all inputs to be of a fixed length. So if you set this too short, you might lose important context in longer prompts, and if you set it too long, you may waste memory or run into device limits, especially on GPUs. D type over here stands for data type, which is used for determining the precision used for the model's computation. For example, it can have values like float 32, float 16, or B float 16, and lower precision types like float 16 speed up computation and reduce memory use but may lead to slightly lower numerical accuracy. Most modern inferences these days prefer float 16, that is FP16 or B float 16. And finally is the load in 4-bit. So by loading this in 4-bit, we can save memory and speed up training dramatically, which is super helpful when using larger models with limited hardware. Alright, so the next part is gaining the HuggingFace token. Now I am accessing the DeepSeek model from HuggingFace, which is why I'm using this HuggingFace token. If by any chance you're using the model from elsewhere, then this line is not needed. Since I'll be loading the model as well as saving the results back into Hugging Face, I'll be needing this. So how do we get this Hugging Face token? For that, you'll first need to have an account in Hugging Face and then click your profile picture over there. Then go to settings and from settings go to access tokens. Over here, you'll have to create a new token in which you can fine grain the permissions, what your token can do, what it cannot do, or if you just want to do it in an easy way, you can just set it to read, give it a token name, create the token, and copy. This is what we will be using. So let's add the secret. Let's then enter value, and we will call this Hugging Face token. Okay, now we have added the secret, and this should run now. Yes, it's working. Similarly, we will need one for 1 dB as well, which is for weights and biases. So the reason we are using this is because our runtime history can be stored over here and we can access it later whenever we want. It's good if you want to do an analysis. Otherwise, if that's not really of your concern, then there's no need to run this step at all. Next, let's load the model and the tokenizer. So we'll be using the DeepSeek R1 Digital Llama 8V model. Next is model inference before fine tune. So we would like to see how it would answer before we fine tune. Now over here, there is prompt style. The reason prompt style is there is to help making an answer in a more predictable manner. It will be easier for debugging later, and it's also a standard way in which it can follow the style. So this is our question, which we'll be using to ask it and get a response from. Fast language model dot for inference brackets model. This is used for inference mode, not for training mode, because we are just asking it a question right now. And then is the inputs equal to tokenizer and so on. This prepares our text prompt, the question, for the model by converting it into token IDs, that is numbers. And return underscore tensors equal to PT means return PyTorch tensors. And to CUDA, which is for the GPU, because we need faster processing. And model.generate, as you know, is just to actually run the model and generate a response. Input IDs and attention masks, these are the numerical input tensors that the model needs. Max new tokens will be the maximum number of tokens that the model will generate in its reply. Over here it's 1200 because we don't need a very big answer, we just want to test how it does. Next is use cache. So this uses key value caching to speed up the auto-regressive decoding, which is generating long text, step by step, efficient. And then final is just the response equal to tokenizer or batch decode. This is the actual response that will come, the answer that the model has generated. Now, if you look at the answer it has generated really carefully, you will realize that the model thinks and then it gives an answer. Well, it should think because it is a reasoning model. But if you look at the answer over here, it's a very general answer. It attempts to give a clinical answer step by step, but it may really lack that domain specificity and common errors can be there. So we are going to fine tune this and then we'll ask it the same question at the end to see how it does. Alright, so let's begin the actual fine tuning. So the point of this code block is to prepare your transformer model using the fast language model API that is from the Unsloth library for fine tuning using PEFT, which is parameter efficient fine tuning, specifically with a method called LoRA, which was said before, that is the low rank adaptation method. So let's break down what's happening here and why it matters. So first, what is PEFT? Parameter efficient fine tuning. PEFT techniques like LoRA allow you to fine-tune a large pre-trained model for your task without updating all of its parameters. Instead, they introduce a small number of additional trainable parameters called adapters, keeping the vast majority of the original model as is. It's like it's frozen as is, and we are not going to touch that at all. So this really makes the fine tuning much more memory and compute efficient, which is a huge benefit when working with large language models. Now next, what is LoRA? So LoRA injects these small learnable matrices into certain layers inside the model for transformers, commonly known as these QProj, KProj, VProj, OProj, etc. and so on. And during training, only these LoRa parameters are updated. The rest of the model remains unchanged as is completely untouched. And at inference, the adapted model can be merged for efficient deployment, or the LoRa weights can just be plugged in on the fly. Okay, so the parameters. Now, the model is the model which we have defined earlier, that is the DeepSeek R1 model. R16 over here stands for the rank of the low rank decomposition for the adapted matrices. Higher means more capacity, but more memory will also be used. Then is the target modules. So this specifies which layers in the transformer will get the LoRa adapters. Here it is the key query value output projection layers that is core to how the transformer attention really works. Then is the LoRa alpha 16 equal to 16. So this scales the LoRa layer. It governs how much influence these adapters should have on the model. Next is the LoRa dropout equal to 0, which is a simple dropout. Over here, we are not applying any dropout to the LoRa adapters. And dropout over here is supposed to help regularize, but that's not a need right now. Then bias none. So we are not adding any bias into the adapter layers. Next is use gradient checkpointing equal to Unsloth. So this activates the memory saving tricks, that is the gradient checkpointing during training, letting you train with longer sequences or larger models. Then is the random state equal to 3407. So this is just a random seed that has been put in so that it can be reproduced in the same manner anywhere else if anyone wants. Then use RS LoRa equal to false. If this is set to true, it uses a much more memory efficient version of LoRa models, of LoRa for huge models, but here it's off. We don't really need it right now. Then is the LOFTQ config, which is equal to none over here. So this allows the further configuration of quantization aware LoRa. It's a bit of an advanced thing. This also we can keep it off for now. So all of this together in plain English is just telling the fast language model API, please set up my current model so I can fine tune it efficiently and cheaply by just learning a small set of extra parameters, that is the adapters, in these core transformer layers. Make it memory efficient and practical for my hardware. And this step is really essential before you actually begin the fine tuning, if you truly want the benefits of PEFT and LoRa. Okay, so now that this is done, loading and processing the dataset. Like I mentioned earlier, the prompt style over here, we are following the same thing. I have a prompt style for fine tuning. And then the EOS token. Yes. So why do we need to store the EOS token? Now, this EOS token stands for end of sequence tokens. Most language models require a special token at the end of each training example to mark where the text or where the answer finishes. So adding this makes sure the model knows that this is the end of the current prompt or current answer, helping it learn when to stop generating text during training and inference. Okay. And over here is the fine tuning dataset that we'll be using. More specifically, it's an instruction set. that is from Freedom Intelligence, where we will be using the medical O1 reasoning SFT set from them, and we'll be taking 500 examples only from that set for the training over here. So let's set up the model. Okay, this is a bit huge, but I'll explain it all one by one. So over here, you can see the SFTT trainer. Now, what is SFTT trainer? So the SFTT trainer is a user-friendly, all-in-one wrapper that manages the whole training process for you. It takes your model, tokenizer, and dataset and handles the details of batching, shuffling, loss calculation, model updates, all of that. Next is arguments, what each means. I'll be explaining all of these arguments. Model again is the model which we defined earlier, tokenizer, max seq length, train dataset, all of these is what we defined earlier. So the data set text field equal to text. So from our data set, the instruction set, which we'll be referring to, in that it has multiple columns and we are just referring to the text column here. So that's all this really means. It just refers to the text column. It tells us which field has the example, which has our final formatted input, that is from the earlier prompt plus reasoning plus answer. That is the answer that is there in the instruction set. Then is dataset num PROC equal to 2. This is just the number of processes used for speeding up the dataset pre-processing. It helps on multi-core machines specifically. Okay. Then is the per device train batch size equal to 2 over here. It's how many examples to process per device, like a GPU per step. Smaller sizes are of course more memory friendly. Then is the gradient accumulation steps equal to 4. Over here, gradients are accumulated over 4 steps before updating the model weights. So it's like simulating a larger batch size without extra hardware at all. Then is the warm-up steps equal to 5. So this is like a gradual increase of the learning rate during the start of training for stable optimization. Then is the max steps equal to 60. That's just the total number of update steps to run the training for. And then learning rate equal to 2e minus 4. So this just controls how fast the model learns. It's like when there's a smaller number, it prevents overshooting, but it takes longer time to converge. For those who know gradient descent, it's related to that directly. Then FP16 equal to naught is B float 16 supported. So this just uses half precision to speed up the training and save the memory if your hardware supports it. Then logging steps equal to 10. It just prints the training progress and stats every 10 steps. That's it, nothing much. Then optim is Adam W underscore 8-bit. So this is the optimizer that is running in 8-bit precision for added memory and speed efficiency. Then weight decay equal to 0.0. So this just regularizes the model to avoid overfitting by penalizing the larger weights. Then is the LR scheduler type, that is equal to linear. That's just the linear rate decreasing, the learning rate decreases linearly during training. And again, seed over here is just the random seed for reproducibility, so that your results can be exactly recreated by someone else if they run the same thing. And then the output directory to store our trained model and logs. Okay, now that is done, the model training. This line runs the actual model training over here, and as we have defined 60 steps earlier, it will run for 60 steps. And it just takes 21 minutes over here, 21 minutes, 57 seconds. So if you really compare it to other techniques using different libraries, they take much longer, while using Unsloth over here makes it take much lesser time. So Unsloth is a really, really great toolkit for this. It's a must use. And then again 1 dB, that's the weights and biases. Now we have finished training after this runs. So we just save the results over here, the run history, the run summary, all of it that has been generated during the fine tuning process is now saved. And this is a link that will be available for us to use. Okay, so model inference after fine tuning. Okay, so it's time for the big movement. We'll be asking the same question again to the model and let's see how it responds. So this is its thinking, the reasoning part, and here is the answer. Much shorter compared to what it gave before fine tuning. Now you may notice a lot of similarities in this answer and the previous answer, but this answer is more to the point and gives an actual proper conclusion. The responses are much more accurate, clinically relevant, and it follows a structured and stepwise explanation leading to the proper answer. So this really demonstrates, the value of fine tuning. There's better reasoning over here on how it arrived at the answer. The answer itself is more reliable, and this is more specific to the complex and domain heavy related questions. So fine tuning has a lot of value. It really makes it a specialized model in your domain rather than just a generalist. If you want, you can even try on another unseen case from the dataset to verify that the model maintains its high quality reasoning or not. Finally, we wrap up by saving our fine-tuned model both locally and to Hugging Face Hub as well. Optionally, you can also merge the LoRA adapter weights with the base model for deployment over here. And that's it. That's a wrap. So today we went step by step through fine-tuning the DeepSeek model for advanced clinical reasoning, from environment setup to data prep to training evaluation, all the way up to preparing it for deployment. And if you found this tutorial valuable, don't forget to like, subscribe, and that's all for now. Bye.